Welcome back to the AI Research Roundup. I am Alex. Today, we're looking at a paper from May 12, 2025, trending on Papers with Code, titled Unified Continuous Generative Models. So, continuous generative models. These are AI systems that learn to create new data, like images, by gradually transforming a simple starting point. Think of diffusion models or flow matching, which take many steps, versus consistency models that take just a few. This paper proposes a single framework to train and use all of them, called the Unified Continuous Generative Models Trainer and Sampler, or UCGM. It achieves excellent image quality, measured by fresh at inception distance, or FID, where lower scores are better, with fewer sampling steps, which are the iterations the model performs to generate an output. It's great to see they've also released the official PyTorch code for this work, so in their repository, you'll find the unified framework for training and sampling these continuous generative models, like diffusion and flow matching, along with all the scripts and configurations needed to reproduce their results. This is super helpful for other researchers looking to build on what they've done. So this UCGM framework is a big deal because continuous generative models, while powerful, often suffer from high computational costs and, well, a bit of fragmentation with different training and sampling approaches. UCGM tackles this with its unified trainer, called UCGM-T, and a unified sampler, UCGM-S. And they're getting state-of-the-art results with this UCGM system. For example, achieving a fresh at inception distance score of 1.42 with just 2 sampling steps on ImageNet. That's remarkably fast. Alright. So this first table really drives home the unified part of UCGM. It shows how well-known approaches like diffusion, flow matching, and consistency models can actually be seen as special instances of this new UCGM framework. The table details how specific settings for what the paper calls unified transport coefficients. These are essentially mathematical guides, like alpha t and gamma t, that dictate how the model transforms noise into data over time, and other parameters like the consistency ratio lambda allow UCGM to mimic these different model types. For instance, a consistency ratio lambda of 0 makes UCGM behave like a diffusion model. Okay, so building on that idea of unified transport coefficients, Table 2 here gives us a closer look at how different ways of transforming data, or different transport types as the paper calls them, are handled within the UCGM trainer and sampler. We see columns for linear, relinear, trig flow, and EDM, which are adapted from existing methods alongside new ones like trig linear and random for testing. For each, the table lists the specific mathematical forms of those unified transport coefficients, alpha t, gamma t, and their counterparts, aught and got. This essentially shows the versatility of UCGM. It can implement various data transformation strategies by just plugging in these different coefficient sets. Alright, so this table 3 looks at sample quality for what's called multi-step generation, specifically on the ImageNet 1K dataset. It compares different methods using that fresh at inception distance score we talked about, and also the number of function evaluations, or NFE, which tells us how many computational steps are needed for generation. What's really impressive is how the UCGM sampler boosts existing models. For instance, improving one model's fresh at inception distance from 1.26 to 1.06, while drastically cutting the number of function evaluations. Then, when models are both trained and sampled using UCGM, especially when that consistency ratio lambda is 0 for multi-step, they achieve excellent image quality with remarkably few steps. Okay, now this table 4 shifts focus to what's called few-step generation, again on ImageNet 1K. This is where that consistency ratio lambda is set to 1, which, as we discussed, gears the UCGM framework towards models that generate images in just a handful of steps. And the results are pretty striking. For instance, using their UCGM trainer and sampler, a 512 by 512 model achieves a fresh at inception distance of 1.75 with only 2 number of function evaluations. And for 256 by 256 images, they get down to a 1.42 fresh at inception distance, also in just 2 steps, which is top-tier performance. So after looking at those performance tables, Figure 2 here gives us a visual peek into how the UCGM sampler actually generates an image. We're seeing intermediate stages of a 60-step sampling process. Each row uses a model trained with a different consistency ratio, lambda, 0 at the top, then 0.5 and 1.0 at the bottom. And as you go from left to right in any row, representing decreasing time t in the generation, you see the image, in this case a parrot, emerge from initial noise into a clearer and clearer picture. This really illustrates the refinement happening. Alright, so figure 3 here presents what are called ablation studies, which are basically experiments where you change individual settings to see their impact on performance, measured again by that fresh-end inception distance. The first chart, A, revisits that consistency ratio lambda, visually confirming how different lambda values are optimal for different numbers of sampling steps, much like we discussed with the performance tables. Then, chart B looks at various transport types alongside a parameter called the enhancement ratio zeta, which is part of the model's self-boosting mechanism. And chart C shows how the estimation extrapolation parameter kappa, another UCGM sampler feature, interacts with sampling steps to affect the final image quality. So from these ablation studies and the earlier results, it's clear the UCGM framework offers a lot of flexibility and impressive performance. The key takeaway really is its ability to unify few-step and multi-step generation into one coherent model, and to do so with top-notch results. This matters because it simplifies the generative modeling landscape, potentially making high-quality, fast image generation more accessible and efficient. Well, that's all the time we have for this AI Research Roundup. Thanks for tuning in, and I'm Alex, signing off.